We talked about slope when we first began, and we talked about how to find slope with rise over run. And if we go back to our textbook here, you can see, nice, you can see that the slope is the rise between one point to get to the next and the run to get to the other point there. So the change in y is here, the change in x. The change in y is y2 minus y1. So if you had this coordinate, y2, and the y coordinate of the first point, you could go y2 minus y1. That would give you the change. And of course, for change in x, x2 minus x1. You okay? Okay. So here are a bunch of slopes right here. A bunch of slopes. This horizontal line right here is, of course, a slope of 0. This slope right here would be a slope of 1 because for every jump in vertical position of 1 unit, you'd have an exact horizontal displacement of another 1 unit to get to the next point. Okay? And so, of course, the more steep you go from left to right, is a higher number in slope. The more steep that you go in the other direction, from left to right, if it's going down, it's a larger number in the negative direction. So here is a slope of -5, right? So you have a rise of -5 compared to a run of +1. It's -5 over 1. Okay? Everybody got that? Okay, first type of question here then, in just exploring this again, and yes, you're right, this is still not a lot of real calculus here. This is just leading you up still to calculus, but just one of the other things I want to remind you of, that this type of question says, if you have 2 points here, and I'm asking you to find the linear function that represents the line that passes through these 2 points, you have to know what to do there. So if we have 2 points here, and one is at -1, -1, that's right there. The other one's at 2, 5, 2, 5. Then we're trying to find a linear function that represents that. Okay, well, if you're pretty careful at drawing a line, it would look something like this, right? It's not a real straight line, but it's pretty close. And you could calculate from that line the slope and the y-intercept and go from there. If you didn't have this diagram, you could still do it. You know that the slope is the rise over the run, which actually is the difference in values for the y, so that's 5 minus -1, divided by the difference in values for the x's. That's 2 minus -1. This is 6 over 3, or 2. Remember, subtracting a negative is like adding. So, that's your slope. Slope of 2. What's the y-intercept? Well, if you drew your line carefully, you might be able to see that, hey, it looks like it's 1, right? But what you could do, too, is go from this point and go, slope is 2, so it's up 1, up 2, over 1, I'm going to have a point, and that does indeed end up right on the y-axis. So your b value is +1. And so you would put your answer as, here is my linear function, y, or f of x, doesn't matter. Okay, that's just function notation that you learned last year. And you would say that that function is 2x plus 1. This is the representation of this line, right there. Now, let's just say that we didn't have this diagram right here. Didn't have the diagram, so you didn't know what b was. Okay? B actually was unknown. So is there any way that you could find B here without drawing it? No? Anyone can remember or think of a way you could do that? Well, here's what you do. This is what you've got so far, right? You've got y equals 2x plus b. You don't know b. Do you have a point, a coordinate for a point that you know is on this line? Yeah, you do. You have two coordinates, 2 points you know are on the line. So guess what? If you put in these coordinates, and we'll use the positive ones, 5 is the y value, and 2 is the x value, guess what? You can algebraically find out what b is. And so b would be equal to 5 minus 4. B is 1. And that's how you could determine b as well. Okay, so let's get to the heart of the matter. And again, we talked about this on the first day, the tangent problem. A tangent line, let's say to a circle, okay? A tangent line is a line that would intercept the circle just once. So this would not be a tangent line. That's not a tangent line because we have intercept 1, intercept 2. It intercepts more than once, right? This is not a tangent line because there are no intercepts. But this right here, and pardon my freehand, but this would be pretty close. If you look at that touch, let's say that touches just one time at this very point, this would be a tangent line. Okay? That's a tangent line. Now the tangent line touches the point, the circle at just one point. If you remember this example here, remember we had the kind of the hill over here, and if you think about, let's just redo that here. If you think about a person standing here, remember that we had a person that's standing on the hill, and they're like conquering the hill, and they go up the hill, but they're getting pretty tired, and they want to know really how steep this is. They could kind of look ahead and look behind and kind of guess. But it's really tough to know exactly how steep this really is at this exact point where they're standing right there. Remember we said that this could be calculated if they knew the height of this point and the height of this point. This slope could be calculated really easily. But this one, not so easy. Why? Because we only have one point in reference. And so the slope of a tangent line, slope of a tangent line, can't be calculated the same way as two points can. Why is that? Well, I'll tell you why that is, because slope is change in y over change in x. If you have 1 point there, 1 point, and there's not 2 points, then there is no delta y. It is 0. Delta y is 0, right? Because where's the change? There is no change. And what's delta x? That's 0 as well. So how do you calculate with only 1 point? That's the tangent problem. So what we have to do is we have to think about this just a little different way. And as I mentioned in the intro, that you may remember, is that what you can do is you can find out what the slope is between 2 points that are really close together. And that slope between those 2 points that are super close together are going to be pretty close to the actual tangent slope. See that? They'd be very, very close. And so you could actually calculate the slope between 2 points that are super close together, and that's going to approximate the slope of the line at just 1 point. And so if you look on page 7, this is the tangent problem. Let's just go on here. Oops. Where is it? Tangent problem. Okay? So there's a tangent line. This P, this line T is a tangent at P. This is not a tangent at P. I should make that distinction. This is a tangent because it touches only once here. Even though this touches only once, it's not supposed to intersect the line like this. Okay? A tangent line sort of is above the line, touches, and remains above. Or it's below the line and touches and remains below. That's the sort of kind of tangent we're looking for. Okay? And so in order to find the tangent of a line at a single point, it gets a little tricky. You see, the tangent line at this point on the parabola, which is this line T, to calculate the slope, one would have to